All right, guys, welcome back. So, third lecture. So, in the last lecture, DC machines and batteries, we had looked at a way we can create a magnet of our own. A magnet, we can create a magnet out of a coil of wire. So, let's do it like this. Let's have our ordinary bar magnet to one side and what we termed as the electro let's have that to the other side. Compare them and see what can we do with a bar magnet as compared to a permanent a bar magnet and electromagnet, right? Okay, so let's draw out a bar magnet, right? It was like so. That was the north, that was the south region. So we had the axis, that's the axis, the magnetic axis. We had fields running like so. Some straying off into the air and some being directed to the south, right? In that direction. So this was the north, that was the south. So on the other side, we had a coil of wire with a couple of turns. And we realized if we have current flowing in that direction, that means that was if we apply a positive voltage to terminal A with respect to terminal B, we will end up with that side being the north if the current flows a certain way, so like so. That means current has to, or actually it has to be the other way around. If current comes, let's see how we've drawn the coil. Okay, it goes like so, it goes like so. So for the solenoid, what determines the direction of the north pole and the south pole is the thumb, whereby now the hands, the fingers are following the direction of the flow of current. So let's say we have it like so. That means the current is going top, above. I mean bottom, top, bottom, top. So it's flowing like so, depending on the way I've coiled the wire, the piece of wire. So right, so that means, so guys, this is why I was stressing the orientation, the point of orientation of everything, the coils, the permanent magnets, if you have them, how the current is flowing in which direction. So orientation, orientation, orientation. So that simply means if current is flowing like so, the wire, depending on the wire I've decided to wind my coil, that's going to be the south, that's going to be the north, right? So it's all about the way the coils are wound and the way the current is flowing through them, right? Yeah, like so. All right. So that's how it is. So with the right hand grip rule around the solenoid, what we call a solenoid. The right hand grip rule around the solenoid goes something like this. So if you want to determine, because it's there to determine the polarity of the solenoid, right? Where is the north and the south pole of that electromagnet? So we've found a way to generate magnetism, or to create a magnet out of electricity and a coil of wire. How do we determine its north and south pole? By tracing out the direction of the flow of current and the way the coils are wound. So the way I've drawn mine, it's like so. That means where the thumb points with the fingers in the direction of the current around the coils, the direction of the thumb denotes the polarity of the solenoid. So this simply means this is a magnet of the sorts. So for ease, let me first draw it like so. So that's interesting. Okay, now let's compare the two. This also has a magnetic axis, right? This has a magnetic. This also has the axis, right? An imaginary line running straight through the north all the way to the south pole of a magnet. So this is a magnet like this one. It also has the ability to attract metals and follow all the rules of magnetism. So if we had another coil of a certain polarity, let's say we had another coil here, which happens to be north and south somewhere. Let's say that's the coil we have, and we get it close to this one, and we get it close to that one in that orientation. So the same rules of magnetism will apply. Like poles of a magnet repel, unlike attract. So it is just like a bar magnet. Where is the difference, or what's the difference? Here is the difference. Let's say we suddenly take away the voltage. So this ceases to be a magnet. Let me just put the voltage back. Let me put the voltage back. Let me draw another one here. So let's say this is the same coil. Now for ease, I'm just going to draw it like so. So let's say that is our north, and that is our south. So if I take away, so this is scenario 1 with the voltage present. That's scenario 2 with the voltage absent, no voltage. This is no supply voltage between points A and B. That means there is no current. That means the current is 0 amps. No current flowing. Here there is a certain voltage, I'll call it VAB, between those two. So here there is no current flowing. So this is just a coil of wire. It is not a magnet. It's not a magnet. It is not a magnet. So guys, when you think about it, we've just found a way to create a magnet that we can turn on and off whenever we see fit, whenever we need to. So unlike a bar magnet is permanent. It's permanent. This is controlled. It can be turned on and off whenever we see fit. Very, very important. So let's have scenario 3. Let's look at scenario 3. So still with the coil wound the same way, right? That's point A, and that's point B. Let's say this time round we flip the polarity. of the voltage, negative V AB. So we flipped the voltage, right? We flipped the voltage. That means if we flip the voltage, the current direction is going to flip. That means now the polarity of that magnet is going to flip as well. So this is going to be our north, that's going to be our south. Here the polarity with the same physical orientation with the same physical orientation. Same physical orientation of the magnet. The same physical orientation of the magnet. The poles of the magnet can't be reversed. Here with the same orientation, the polarity is reversible. The polarity is reversible. The polarity is reversible by simply reversing. That means physically I don't have to change the magnet to have an opposite polarity. I don't have to physically reorient the coil. With a permanent bar magnet, if you want to flip the polarity, please, you have to flip the physical orientation of the magnet. You have to physically flip it around. With an electromagnet, we've seen that we do not need to do that. We just need to flip the polarity of the voltage. What was the south before becomes the north pole. Very, very important. Very important in machines, mostly to the DC machines and batteries course unit. Very important principles that become a serious frontier for students when they are going through this course unit. It's simply because they tend to have a wrong mentality that what they covered in their previous levels of education, high school, and what that information is useless. But guys, guess what? Those are the very basic principles onto which we build and we make bigger and more complicated principles. So things like armature reaction, interpoles, we will look at that. I don't want to get ahead of myself. So we will look at that stuff will become very easy to understand and internalize and digest and pass our exams and then go to the field and practice these things in rewinding workshops and repair workshops. So we will get to utilize that information very, very well in the consequent lectures. Only after having understood these basic principles. Very important. So let's talk about one last thing. That is the magnetic field strength. Let's talk about the magnetic field strength. Let's talk about the magnetic field strength B, commonly known as, denoted with the letter capital B. So, magnetic field strength is a measurement mostly conducted in held in Teslas, right? That's the unit in Teslas. It just denotes how much electric fields or flux lines are concentrated in a section area, in a given area. So how well a magnet will perform is mostly determined by the magnetic field strength, or capital B, recorded in Teslas. The SI units, the standard units is Teslas, right? So let's talk about how strong these magnets can be. So this the permanent bar magnet, its strength is determined on the time of manufacturing it or designing it, right? Building it and constructing it. The field strength, the field strength, the field strength of an electromagnet, a controllable magnet, right? A manipulatable magnet is proportional to the current flowing through it. The more current that flows through that conductor, the stronger the magnetic fields, right? The stronger the magnetic fields around it, guys. So the stronger the magnetic field. So guys, now we are getting into the technical stuff now. We are getting into the technical stuff that affects DC machines and batteries. So the magnetic field strength, we've realized, is proportional to the current flowing through the coil. So if we find ways of manipulating the current through that coil, we can manipulate the strength of that magnet, right? Very, very important. The strength of the magnet can be easily controlled by controlling the current. Guys, for those who attend my power electronics classes, this is one of the good applications. Remember, we said if you want to flip the polarity of such a magnet, we just have to flip the voltage, the supply voltage, the applied voltage. We just have to flip its polarity as well. But physically in real world, we are not going to do that. We are not going to be flipping wires and around battery terminals. We have power electronic circuits for that. We have like the H-bridge, a famous H-bridge circuit that can flip the voltage of a coil or whatever load you connect across it. So power electronics can come in handy. Current control, we will look at circuits that can control current. So guys, for those who attend my power electronics classes, we have circuits that now do such things, right? So we know that we can manipulate the current, to manipulate the magnetic field strength. The other thing, this field strength is proportional to is the number of turns around the coil. Number of turns. That is not an easy parameter to manipulate. That's not an easy parameter to manipulate. So imagine you've already designed your motor or generator or whatever, coil or solenoid valve or whatever, and you're trying to unwind and rewind as you're using the device. That becomes impractical. But the practical way is to manipulate the current. So physical parameters of the coil, like the area, the cross-section area of the coils, the number of turns, those parameters aren't easy to manipulate as it may seem. And it's not practical. So the practical way is to manipulate the current. So remember, current has a relationship with voltage. Sometimes, in most cases, it's not to our best interest to change the voltage. Because in real world, it is really hard to find one device using its own voltage source and another device creating its own voltage source. It is common to find that one voltage source supplies a number of devices. So to manipulate it is like rendering the fate of other devices that share that voltage shaky. So what we do is to change the current without changing the supply voltage. How do we do that? So guys, let me wind up with this. So let's say this is the coil. We can add a resistor, a variable resistor, by the way, in series with it, with a certain supply voltage. By changing the resistance, we change the overall current, hence changing the magnetic field strength in that coil. By changing the polarity, now we can change the magnetic polarity. By changing the voltage polarity, we can change the magnetic polarity as well. So these things become more interesting the moment you grasp the basics. So we are yet to see what happens now. We've concluded that a current carrying conductor develops a magnetic field around it, and that magnetic field can be strengthened by increasing the number of turns. We make more turns. We've seen how to deduce the direction or the orientation of the poles, the magnetic poles of such a magnet, because you will have created a magnet, and this magnet can easily be turned on and off whenever we want. We can turn it into a magnet or completely take or deprive its magnetic properties by just taking the supply voltage away. We've realized that if we flip the voltage across that coil, the polarity of that coil flips as well. We realize that the strength of that magnetic field can be manipulated, unlike a permanent bar magnet, guys. So we'll see machines that depend on permanent magnets. These are machines with a very little control, very, very little control, because a huge portion of them is fixed. The field strength that was designed with the permanent magnet is all you have, is all you're going to work with, right? Is all you're going to work with. There is nothing else you're going to add. And if not handled right, the field strength could drop. Yeah, we'll see what affects magnetism in a permanent magnet. So we've seen that, guys. I'm going through conclusions. So we've seen that with clever circuitry. So now you remember why we had the KVL, KCL, that is in the first lecture, those principles stated out. Now we're having loads in series that have a common supply voltage. That means we're going to have individual voltage drops across the coil and the resistive load, or the rheostat, or the variable resistor. So, or a potentiometer if the motor is that small. All right, so by just changing the current, we can change the field strength. That means we have a magnet whose parameters can easily be controlled by changing the electrical properties of that coil. Guys, allow me to stop here. Let's meet in the next lecture, where we are going to be looking at things like Lorentz force, hence the motor effect. We will look at the generator effect, where we'll look at the Fleming's right-hand rule. For the motors, we'll look at the Fleming's left-hand rule. Now, how do we use this information to make a machine? How do we efficiently turn electrical energy to mechanical energy and do some serious work? Crushing stones, driving air around, cooling systems, conveyor belts. We will look at different applications. So thank you for being great learners and listeners. Let's meet in the fourth lecture.